Hello everyone, welcome to the last minute revision for IL Unit 5 exam. So I was wondering, how do I exactly make this video? So initially I thought I'll just solve Jan 24, but then I realized that this exam was literally in the last session and they're not going to repeat all of the questions. So what I've done here is compiled questions, important questions from all the recent years, Jan 24, October 23, June 23 and Jan 23 in this video. So first let's take a look at the structure of Unit 5. But before that, I have compiled literally all of the most common question and answers into a PDF that you can download in the description below, and you get a compilation of all the formulas for Unit 5 with this completely free, complimentary. This will be extremely beneficial for your exam tomorrow. I promise you, you won't regret this decision. Now let's take a look at the topics for Unit 5. So first we have thermal physics, then nuclear physics, oscillations, which is basically simple harmonic motion, and then astrophysics. So for thermal physics, the first section we'll be looking at is from a question from October 23. Let's look at the question. Air is used to inflate a balloon. The inflated balloon has a volume of 1.77 times 10 to the power minus 3 meter cube and contains 5.15 times 10 to the power 22 air molecules. The air inside the balloon exerts a pressure of 1.15 times 10 to the power 5 Pascal. Calculate the average kinetic energy of the air molecules. So the very first thing you have to do is find out the temperature using ideal gas law, using the equation PV equals to NKT. So you have the value of pressure, volume, number of molecules, K is the Boltzmann constant, and T is what you have to find out. Make T the subject of the equation and you get the value of temperature. Then plug in the value into the equation for kinetic energy, equals 3 by 2 kT, and you get the value of kinetic energy. Next you have specific heat capacity and latent heat. So here the question says there are 6 compartments of an ice cube box, and one compartment has a mass of 0.022 kilogram, right? The question says all 6 compartments in the ice cube tray are filled with water to a depth of 3.5 centimeter. The ice cube tray is placed in a freezer. The initial temperature of water is 22 degrees Celsius. It takes 12 minutes for all of the water to become ice at 0 degrees Celsius. So there are 2 things going on here. The freezer does 2 jobs actually. One is lower the temperature of water and then freeze that water into ice. So whenever you get a concept of temperature change associated with energy, the equation is E equals mc del theta. So for del theta, the initial temperature is 22 degrees Celsius and the final temperature, the lower temperature, is 0 degrees Celsius. You find out this energy, and then the freezer does another job, that is to change the state of water in these ice compartments into ice. So the equation is del ml. Whenever you have a question associated with state change, the equation is always del ml. So the total energy that the freezer supplies is this energy plus this energy, and we all know energy equals power by time. Power equals to energy by time. So these are the 2 energies divided by time was given in the question. Time was 12 minutes. Of course, you have to convert minutes to seconds. So this is the power. The question said The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watt, but your calculation says otherwise. It says it transfers energy at a rate of 78.5 watt. So the claim is not correct. Next up, in thermal physics, you have gas laws. A tire on a racing bicycle contains nitrogen at a temperature of 22 degrees Celsius. The nitrogen in the tire has a volume of 2.85 times 10 to the power minus 4. The pressure of the nitrogen in the tire is 5.75 times 10 to the power 5 Pascal. Nitrogen pumped into the tire. The volume of the tire remains constant, so volume stays the same. The total mass of nitrogen in the tire, including the added nitrogen, is 2 gram. Calculate the increase in pressure of the nitrogen in the tire. Assume the temperature remains constant. So gas laws used to be very straightforward, but recent years they have also seen that everybody is getting this right. So they are twisting the question a little bit, but please don't be alarmed. When you look at these values, just plug in the values in our ideal gas law equation, PV equals to NKT. And from here, with the initial values, you find out the N. Then, using this N, you find the new pressure, right? Using the same equation. So this is the new pressure. What was the initial pressure? Initial pressure was 5.75. And the question asks the increase in pressure. So increase in pressure would be new pressure minus initial pressure. Then you have internal energy. Every time a question asks you about internal energy, it's always a good practice to start with the definition of internal energy. Internal energy is the sum of molecular kinetic energy and potential energy. So this is a very important point. And when something is cooling, the internal energy always decreases. Internal energy decreases. So as the temperature of the wax decreases, the molecular kinetic energy decreases, because kinetic energy depends on temperature. As temperature decreases, kinetic energy decreases. So that's what decreases the internal energy. But between X and Y, you can see temperature remains constant. Always remember, the temperature remains constant during state change. So between X and Y, the liquid wax is solidifying and the molecular potential energy decreases. So when something is freezing, potential energy decreases, and when something is melting, potential energy increases. You can use that for other questions in your exam. I repeat, when something is freezing, molecules are coming together. So that's what decreases the potential energy. And when something is melting, molecules are moving apart. So that's what increases the potential energy. Now, between times X and Y, the temperature is constant. So there is no change in molecular kinetic energy. Like I said before, kinetic energy depends on temperature. If temperature is constant, kinetic energy is also constant. And at Y, the wax has solidified. Then you have thermistors. This is somewhat of a topic from Unit 2 actually, but it's a cross-unit question. So thermistors can be used as temperature sensors. So let's see what the question says. A student is planning an experiment to investigate how resistance of a thermistor changes with temperature. The student wants to use temperature range of 0 degrees Celsius to 100 degrees Celsius. Describe a method the student could use to determine the values of resistance and temperature. So you have to find out the values of resistance and temperature. You should include one precaution. So the very first thing you do is use a thermistor connected to an ohm meter that will directly measure the resistance. Now place the thermistor into a water bath. Cool down the water bath and then start heating it. You have to add ice to the water bath to bring it to 0 degrees Celsius. Otherwise, just a water bath will be at room temperature. You have to lower it to 0 degrees Celsius using ice. Heat the water and use the thermometer to measure the temperature. Measure the resistance for each temperature by reading from the ohm meter. Star the water to ensure the thermistor is at the temperature of the thermometer. So if this question specifically said you don't have to draw a diagram, but in your exam they might ask you to draw a diagram of the apparatus. So this is what you draw: a thermistor connected to an ohm meter. This is the symbol of an ohm meter, and you have to use a thermometer, and this is a water bath, and this symbol is for heating. In nuclear physics, moving on to nuclear physics, look at this diagram. This wasn't given in the question. I specifically added this to give you a better understanding of this question. So this is a radioactive source. This is a measuring, not a measuring, this is a detector, a Geiger-Müller tube. And between these two, you have an absorber. And this specific question is dealing with the thickness of this absorber. So the thickness determines the count rate, and they are related by this equation. And when you plot a semi-log graph like this, you get this graph. In the same question, they said the mu and photon energy are related by this graph. I want you all to specifically look at the axis, y-axis of this graph, where you see 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. But from 10 onward, this is 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. What do you call this graph? This is a logarithmic, not a graph, this is a logarithmic scale. So you can include a wide range of values in the axis. So if a question asks why would you use a logarithmic scale, this is to incorporate a large range of values. This is exactly what we do when it comes to HR diagrams, the temperature scale, that is also logarithmic. So from here, let me break this down actually. Let's see, R equals R naught e to the power minus mu x. When you take ln on both sides, so ln R equals ln R naught plus ln e to the power mu x. So ln R equals, bring this forward, minus mu x plus ln R naught. And look at the axis, this is ln R naught against x. So this is in the form y equals to mx plus c. You have ln R in the y-axis, x in the x-axis, so the gradient of this graph will give you minus mu over here. Gradient of the graph will give you minus mu, and you look up the value of mu over here. So this corresponds to 70. So this is mu is 60, right? So 10, 20, 30, 40, 50, 60, somewhere over here, and this is the value approximately. Then we move on to nuclear physics, radioactivity. A sample of pure CS has an activity of 7400 becquerel. Calculate the mass in kg of the sample. Half-life is given, mass of CS is given, and atom is given, and the value of 1 year in seconds is also given. So the moment you come across half-life, just recall the equation T half equals ln 2 by lambda. If T half equals ln 2 by lambda, lambda would be equal to ln 2 by T half. So you find out lambda. For this, dN by dt is basically activity. So activity equals to minus lambda m. At this point, let me remind you, please make sure you have all of the equations memorized. During your exam, you cannot be looking back at the end of your question paper to recall the equations. You have to have all of the equations on the tip of your tongue. Then you find out n. You find out that this is the number of atoms. If one atom has a value of 137 U, U is unified atomic mass, then 1.02 times 10 to the power 13 would be equal to 1.02 times 37, but that would be in U. But you have to find out the mass in kg. That's what's specifically said in the question. So how do you convert U to kg? Multiply it with 1.66 times 10 to the power minus 27. Do not mix it up with the mass of a proton, which is 1.67 times 10 to the power minus 27. I see a lot of students confusing U and mass of a proton. Then you have binding energy in nuclear physics. Binding energy in calculations can appear both from the context of fusion as well as fission. So this question from June 23 is from the perspective of fusion, but the next one from Jan 24 is from the perspective of fission. So the question says, determine the energy in MeV when a nucleus of deuterium fuses with a nucleus of tritium, H3. So look at the binding energy per nucleons. Binding energy per nucleon of deuterium is 1.1 MeV. Binding energy per nucleon of tritium is 2.8 MeV. And the binding energy per nucleon of helium is 7. You have to refer to this equation. So these are the reactants, these are the products. So binding energy is always associated with del M, which is the mass defect. So this is the product and these are the reactants. When you subtract the energies corresponding to the mass defect, this is the energy released. So this actually comes from E equals del M C squared. So this specific question did not specify about mass defect. It is just the difference in energies. But this difference in energies actually correspond to the mass defect del M. You might need this in your paper. So this was binding energy from the context of fusion. Now let's see binding energy from the context of fission. Nucleus of uranium undergoes fission. One of the fission products is Sn. Estimate the energy in MeV released in the fission. More or less the same thing. So when you look at the binding energy per nucleon of uranium, this value is around, this is 6, this would be 7, so somewhere between 7 and 8 is 7.5, and the binding energy per nucleon of Sn is, this is 8, this is 9, so this would be somewhere between 8.5. So the increase in binding energy per nucleon would be 8.5 minus 7.5, that is 1 MeV. So that would be binding energy per nucleon. But we have to find out the energy, not the energy per nucleon. So what do I do? Multiply it with 238. So that would be the energy released. Next we move on to oscillations. The first question would be from Jan 23. At a particular speed of the car, resonance occurs. So guys, the question specifically mentions resonance occurs. So in this type of questions, resonance occurs is actually a marking point, but for this specific question, since the question itself specifies that resonance occurs, writing explicitly will not get you any marks. So the question says why the amplitude of vibration increases. So the car body is driven or forced into oscillations at its natural frequency. So resonance occurs and there is a maximum transfer of energy to the car body. I'll skip this page and go to the next one. This is from June 23. Look at the question. She observes that the amplitude of oscillation increases, but this question doesn't specify that resonance occurs. So for this one, resonance occurs would be a marking point. This is a very common question which I have already covered in the frequently asked questions compilation. Now let's go back here. When a person of mass 65 kg steps into the car, the vertical height of the car above the road decreased by 2.5 centimeter. Resonance occurs when the speed bumps are placed 25 meter apart. Calculate the speed. This is a very complicated question at first glance, but it's not. Just follow the steps and you will arrive at your answer. Calculate the speed of the car driven along the road. You should consider the car as a mass spring system. Mass of empty car is 1300 kg. So we all know F equals kx. So F would be the weight of the person, right? F would be the weight of the person. And x is 2.5 centimeter. So from here you make k the subject of the equation and you get the spring constant. Then you use the equation T equals to 2 pi root over m by k. So k remains the same, but this time the mass would be mass of the car plus mass of the person because they oscillate together. You find out the time period. So let's look at this question. So I have a speed bump here and I have another speed bump here, let's say. And these speed bumps are placed, question says, 25 meter apart, right? So from here to here, the time period that we just found out was 1.45. The distance divided by this time period will give us the speed of the car. The question was very layered. We already covered this. Let's move on to astrophysics. Light from stars and distance to stars. Pluto is a dwarf planet in the outer regions of our solar system. Pluto moves in an approximately circular path around the Sun. The mean radius of orbit is 5.91 times 10 to the power 12 meter. Calculate the intensity of radiation from the Sun incident on Pluto. Radius of Sun is given, temperature, surface temperature of the Sun is given. So I have to start somewhere, right? So it's better if I just draw the diagram. This is the Sun, and here I have Pluto, which is in orbit around the Sun. Okay. So what do I have here? The mean radius of orbit is 5.91. So this is the radius of orbit, which is also the distance, by the way. and the radius of sun is given this. So with using this, you find out the area, surface area of the sun, because the radius of sun is given. This is the radius of the sun. You find out the surface area of the sun. And you might be wondering, why on earth do I need the surface area of the sun? You need that to find out the luminosity, which we'll use to calculate the intensity. So luminosity comes from Stephen-Boltzmann law. L equals to sigma surface area times t to the power 4, and t is also given over here. With this you find out the luminosity of the sun, and then you use inverse square law to calculate the intensity. Just plug in the value of luminosity over here, but this d is actually this distance. Intensity depends on the distance and luminosity depends on the radius. So a lot of times you'll see this d and r used interchangeably. Bear in mind, when it comes to intensity, it is the distance, and when it comes to luminosity, it is the radius of the luminous body. So here this is r, so L equals, the full equation is 4 pi r square sigma t power 4, and for intensity it's L by 4 pi d square, and this is the d we use for intensity, this is the r we use for luminosity. I see a lot of students getting confused with this d and r because you have 4 pi r square and 4 pi d square here. They find this a bit confusing. Then we have to link gravitational force and centripetal force, and this is the question from Jan 2024. Calculate the time in years that Pluto takes to make one complete orbit of the sun. So if you look at this, Pluto is orbiting the sun, right? So for anything to orbit something else, it needs centripetal force. And where does this centripetal force comes from? The centripetal force comes from the gravitational force. So Fg equals Fc. So gravitational force, equation for gravitational force is gmm by r square. Equation for centripetal force is mr omega square. You might be wondering, equation for centripetal force is also mv square by r. Why did we not use that one? Because using mr omega square, you can easily find out the time, because omega equals 2 pi by t. And in this equation, the mass of Pluto is not given because you don't even need the mass of Pluto. This small m is actually the mass of Pluto, which gets cancelled out. Next, we have to link Wayne's law and Stephen-Boltzmann law. Betelgeuse is a red giant star with a luminosity of 4.49 times 10 to the power 31 watt. The peak intensity of radiation from Betelgeuse occurs at a wavelength of 850 nanometer. Guys, the moment you see peak intensity of radiation, right, just recall the equation for Wayne's law, which is lambda max T equals constant, and the value of the constant is actually 2.898 times 10 to the power minus 3 meter Kelvin. Okay, so lambda is given, lambda max. Always remember, lambda max is the wavelength at which peak radiation occurs. Lambda max is not the maximum wavelength. I see a lot of people mixing up these two concepts up. You make T the subject of the equation, you find out the temperature. Then you bring in Stephen-Boltzmann law. Luminosity of Betelgeuse and luminosity of the sun. You plug in the values and you separate the R's, and the ratio you get is the ratio of Betelgeuse to ratio of the sun. which is around 1000. And finally, we have HR diagram and stellar evolution. PQR, this is a question from Jan 24. PQR and S refer to different areas on the diagram. Describe a possible evolutionary path for stars originally in area P. For each stage in the path, you should refer to type of star. So you can clearly see P is on the main sequence. This is the main sequence, right? So stars in area P are massive main sequence stars. Why are they massive? Because they have a large luminosity, and only massive stars can have large luminosities. These stars over here are also main sequence stars, but they are not massive stars. They are actually low mass stars. So stars in area P evolve into area S, and stars in area S evolve into area Q. P are main sequence. What is S? Red giant. And eventually they end their lives as white dwarfs. Now a question may ask you, what do you mean by a main sequence star? What does a red giant star mean? What happens in a red giant star, and what's going on in a white dwarf? All of these are also covered in the frequently asked question booklet. Good luck with your exam. Thanks for watching.